Good evening and welcome to this evening's lecture. Um, I would like to talk about interfaces. Specifically, I've had questions on how interfaces are implemented or created, and I'd like to take a moment just to describe a general implementation and for interfaces or a particular usage model. What you'll see here is the Wishbone standard. It's on Wikipedia. Realistically, you can Google this, Bing this, whatever you like, and you'll find that an open standard. It's an open protocol. PCI, for example, is a protocol that allows PCI devices to talk to one another. ARM or AHB, ARM has its own actual protocol that allows ARM devices, ARM periphery devices, APB, to actually communicate with each other. So everybody has a protocol. Wishbone just happens to be a free one, so since I don't want to have to pay to use it, we're going to use this one. And what you'll see is it allows me to have a topology. I can have a bunch of devices talk to each other. Now, why do you need this? Well, realistically, you don't want to have to string together a bunch of custom interfaces to talk to different designs. You want to have a guaranteed communication protocol. So, for example, I can send someone off and they'll design a USB core, and how can I get it back into my computer chip? How can I make it integrate seamlessly? Well, the idea is if we all follow a common protocol, we can then take and put a video decoder in there, and it will be able to talk on the same bus. And then I can put a display controller on there and inside my SoC. What this gives me is a flexibility to add elements to my design without having to reinvent the wheel every time. So now that you get the idea sort of why we use protocols, let's talk about interfaces. Interfaces are a way to actually capture these protocols, or rather the signals, and bundle them into an easily expandable structure. So let's take a look here. Here's what the Wishbone looks like. If I had a Wishbone master and a Wishbone slave, they would be connected as such. We'd have two common signals that both units see, the reset and the clock, and these come from your system controller. Now, the address out of the master is obviously the address in of the slave. The DAT in is obviously the DAT out of the slave. So the idea is wherever I'm driving from the master, the slave is receiving. Whatever I'm driving from the slave, the master is receiving. For example, to indicate that data has been captured or I have seen a cycle, I use the cycle. To acknowledge that I have actually taken in the data, I send an ACK. Okay, so when the slave says I've seen the data, I issue an ACK. To say that I'm sending data, the Wishbone master asserts a strobe. There's a communication protocol. We can delve into it further, but today we're just going to deal with the pins that are common, and the direction. So SystemVerilog allows for the concept of an interface. It turns out these pins are all the same, they just have different directions. What if I was to have a data type, an abstract data type, that allowed me to bundle these signals into something meaningful? And for example, what if somebody decided that they wanted to add a new signal to this called tag? So tag might be a way to keep track of the transactions. For example, I might have a delayed completion interface, meaning, or a split transaction interface, meaning I will have some transactions happen out of order. And how do I keep track of the order in which they're occurring? I give them a specific tag. This is a very common technique to allow us to split up the traffic. So what I want is I want the ability to extend this interface too, but have everybody see these new signals. So, for example, if PCI 2.0 to 3.0 added new signals, we want the ability to grow the interface and everybody see it. Okay, now the problem is propagating these changes manually to each of the designs is error prone, and we want to have a uniform way to do it. So SystemVerilog gives us the concept of interfaces. What are interfaces? Interfaces are an abstract data type that actually act like a module that sit in between you and your design. Okay, so the idea here is there's a set of common signals, and they'll actually exist within the interface. Now, to give them direction or to actually associate them with a particular input or output, we create what are called mod ports. Mod ports allow us to define the direction of data. So we say that there is an address object inside the Wishbone, and the question is who's driving it and who's driving it, who's receiving it. Okay, how do we actually define direction? Now, an interesting thing about Verilog is Verilog wasn't exactly the strongest in guaranteeing you didn't assign inputs to outputs in modules or outputs to inputs. Interfaces are a very strong structure. They strongly type, or rather, they strongly check whether or not you're assigning inputs to outputs correctly, and you're assigning everything up, you're connecting everything up correctly. Why is this valuable? A lot of people misconnect signals, misunderstanding the names. If a poor name was used, they might think it actually goes somewhere else. This will guarantee you don't make those mistakes. So you'll notice I have two common signals, the reset and the clock. Now, what we're going to find out is Wishbone also allows us to propagate common signals outside of the mod port definition, or rather along with the mod port definition. So, because realistically, I don't want the mod port to be driving my reset or my clock. I don't want either side. So what I'm going to do is I'm going to go over an example design I've come up with that implements this Wishbone interface. And again, the idea here is just to provide a connection mechanism, okay, that allows us a clean interface. Now, a clean hooking up, if you will. Now, what makes this important also is I don't actually have to have in my design, I don't have to have the slave side ready yet. I can actually just connect up my master, and I can actually have tasks exist inside my Wishbone interface, and these tasks can actually provide reads and writes. So the interesting thing about this is my interface can actually act like a bus functional model if I so choose. So I can stage my design to be more modular, so I don't actually have to have the end product complete before I actually design either side. So let's look at the example. It's enough dialogue, let's just kind of get down to the nitty-gritty. So what is an interface here? Well, in this example, I have a Wishbone interface. I've called it Wishbone interface. That seems like an appropriate name. Now, here's the thing. Wishbone says I can be an 8-bit interface, a 16-bit interface, a 32-bit interface. I don't necessarily know. I might decide that we're going to go 64-bit next year with our product line, or we might want to go 128-bit. So if I create my interface if I'm very forward thinking in how I define an interface, I can actually make this grow with my design. And I don't have to rewrite the code, I don't have to really go through and change anything. Everyone scales with it. So I can have what's called a parameterized interface. And here I'm saying the parameter is of width 32. Okay. Then I have, these are global signals. These are signals that have no real direction relative to the master or the slave. They always are the same, right? They're always going to be the exact input or output of either port, and they actually should be an output, if you will, because they're going to be output to the modules. So that brings up an interesting point, is that when we look at this, you have to think about what is the direction of connectivity. So if I bring this up next to my picture, the question is whoever's connecting to this the master, so this is the master mod port, the question you have to ask yourself is, what direction is this? Okay, so if we look at this, the address is an input to us. So let's go ahead and start coding this together. Let's just say, what would our mod ports look like? I just put this up as an example, but let's write this. So when I write this, I gotta say, what are the directions? So we'll say mod port, master, and let's ask ourselves, what are the inputs? The inputs are going to be our address. Now notice our address turns out I don't need to say output or input like they say on the Wishbone protocol, because that's kind of meaningless. Realistically, to us, it's an address. It's going to become a connection address that connects between the master and the slave. So we have an input address. We have an input write data. Now, what is write data? I actually called it write data because it's an appropriate name. It's our data out. It's the data we're writing from our Wishbone interface. And what else do we have as an output? We have write enable. Again, we can skip these output and input. If you add these into your mod port, it's all going to get very confusing. Now, because realistically, the directions are kind of reverse of what you think. Because we're taking these as an input into us, okay? We're acting almost as if we are the slave that we're connecting to. So let's continue. So select and strobe. Okay, that is our inputs. Now our outputs are going to be the DAT, the read DAT. Turns out when the slave sends data, it's actually outputting data, right? It's the data we're reading from the interface. Okay, now we also have our ACK and our cycle. Okay, so now we've defined a master interface. Tools, compile, let's see. Did I get it right? It looks like I did. No errors. Surprises me every time too. So, now we're typing again. Now let's make the slave interface. Let's go look at this guy. What does this guy look like? We almost don't need to see it. We kind of already know the answer to this. It's going to be the exact opposite, right? It's going to be the exact opposite of our master. And so, but let's just do this. Let's just go, and you might notice I've missed something. I'm going to come back and get my global inputs, right? I'm going to come back and get my clock and reset. Let's take care of that. Let's take care of the main inputs first. Address. Okay, now what is going to be the data that's going in here? It's going to be our write data. The write data is going to be an output. So let's get our outputs. That'll be easier. So adder, write dat, write enable, select, strobe. Okay, so what are our inputs? This should be relatively straightforward. Our inputs are going to be, I'm sorry, yeah, so our inputs are going to be, and remember, we got to think about it from what am I driving right here on this slave. Okay, so if you look at it, we're outputting address, we're outputting write data. Okay, we're taking in read dat. Okay, we're also taking in ACK and cycle, and basically it should look exactly like the counter of the master, and it does. I think we got this right, so we'll compile again. Well, not code coverage. Whoops, too fancy for this lecture. Compile. Oh, undefined port. That's because there's not enough D's. Okay, tools, compile. Okay. So, kind of a misleading little command line there, but the idea is if you don't see any errors after it, you're good. I usually do it clear. This way I can kind of make sense. So, tools, control, yeah, okay, good. So, we're doing good right now. Okay, now, this is our interface, but we're missing something, right? We're missing the clocks. Now, the part, as our output, it's going to be clock. Now, and I chose a poor name. Let's rename this clock I. Again, I don't like that. I just was kind of following the Wishbone spec. Realistically, a clock and a reset are output from both. Okay. So, and you can kind of see this from the block diagram, right? These are inputs to the top level. They're from the system controller, and they are outputs. Okay, so now we have a master and a slave. So let's go and build our test bench. So let's fake a system controller. Our system controller is nothing more than just a clock and a reset in this instance. If you look here, I'm not following any rules here. about proper clock and reset generation because we're going to use clocking blocks soon. Clocking blocks will solve the majority of proper clock and reset generation. But how do we instantiate this? So what I do here is I create a module. By the way, interfaces cannot be instantiated in program blocks. They can only be instantiated in modules. Okay, so this means we will need a mechanism in which to propagate the interfaces throughout our test environment. And we'll talk about that. We'll talk about handles. So now the idea is I have a Wishbone interface. I instantiate it. I'm actually, like I said, it's like a module. I'm actually instantiating it, and I'm giving it the global input clock and reset, and I'm giving it a name Wishbone. And so how do we talk to this? We basically say Wishbone dot master, Wishbone dot slave. Okay, and if we want to talk to any specific signal, we say dot read dat dot, or we can just say dot write enable, and that's how we can assign values. So if I wanted to assign values to the master, write directly onto the master interface, I would look at what is, whoops, let's scrunch this up a little more even. I would say, okay, well, what signals are available? Well, as an output, or an input, if you will. So I would say, write master strobe is equal to 1. And what would this do? This would drive the input signal strobe. Now strobe would then propagate through the slave interface and onto the strobe input. This is sort of how interfaces work. It doesn't seem to have much value other than just getting in between modules, but let's take a step back and let's think about how I might use this interface for more than just creating a very common, clean set of port definitions. Let's look at the concept of handles. So when I have this large test bench environment, and let's look at what a large test bench environment might look like. Our large test bench environment will have a top level test bench. It'll, TB. Let's just call it something creative like that. Okay. And inside there, inside our test bench, we'll have a program module. We'll have our interfaces, right? So we might have several, just say Wishbone if inst 1. Okay, and we might have 5 of these. Who knows? We might need a bunch of these. Now, inside, and we have our DUT. Our DUT might actually connect to, so this might be our DUT, and our DUT might actually connect to these interfaces. Okay, and so we want to be able to drive data. We'll have actually several testers, several drivers. Okay, but where do those drivers come from? Those drivers come from our environment class. So we're going to have an environment class that exists, that instantiates our receiver, our scoreboard, our driver, right? So we have our environment class. Okay. And inside our environment class, we're going to have a driver, we're going to have a receiver, and we're going to have a scoreboard. Scoreboard's sort of the goalkeeper, if you will. He says, keeps track of all the good stuff, the bad stuff. Okay. You really don't need that. Okay, scoreboard. Now, what happens here is our environment brings up all these interfaces, or it brings up everything. It basically brings up the driver, the receiver, the scoreboard. But our driver, receiver, and scoreboard need to communicate. Okay? They need to communicate with our Wishbone interfaces. Okay, and let's just say Wishbone interface master. Let's just make it simple. Okay, and so we're gonna have somebody be a master onto this, and maybe there's some output. Okay, let's just say master 1, and we'll just make it 2. Let's not make it too complex. Okay, now the driver is actually going to be pushing data into this. He's going to be driving data into the interface, which will then drive data into our DUT. As it does that, it'll actually drive data into the scoreboard. It'll send a copy. Let's see if we can't get some arrows onto this to make it a little more clear. Okay, so, and then you'll see the exact same thing happen for the other. And so let's just make a copy here. And let's say, simple enough, right? And everything works. Now, the problem is, how do you actually mechanically do this? What are the mechanics for connecting this up? Okay, and let's just cover this real quick. We might have a receiver that takes data, that captures the data on the output of the DUT, and it might also too have an interface. Okay, and it's going to send a copy of whatever it sees to the scoreboard, or it'll compute something and send a computed version of that to the scoreboard. Okay, now let's think about this. How do I pass these? How can I, from my test bench, if you recall, how from my test bench can I send these signals all the way into my interface, into my driver? So let's say I have a program test, and let's just say it was called test, and I want to actually send my interface into it. Well, if I actually just passed WB into the test, say this is a program test, and I said just Wishbone interface, Wishbone IF WB, what's going to happen? What does this actually do? Let's put these closer together so it might be more obvious. Okay, this actually says instantiate an interface inside the program. Okay, well that's not good. It's going to say instantiate an interface within the module ports. What does that mean? That means that this guy right here, let's just go ahead and grab him, gets put right there at the interface. And maybe we need a really small version of this to make it clear group. So we have our, and let's just shrink the font. Yeah, that's good enough. The points, that's kind of abstract there now, isn't it? Okay. Okay. So what do we have here? Once I do that, if I call my program test, okay, and my program test, I kind of, let's just say it actually encompasses, it's the one that creates the environment. So let's say it actually looks something like this. Okay, and let's just send back. Okay. Whoops. Okay. So let's just say this is my test. Okay. By basically just saying Wishbone interface and declaring it there, I'm actually saying that put another Wishbone interface here. So we declared a Wishbone interface here. We declared a Wishbone interface here. And what did I do here? I basically said create an interface here. Well, that's kind of a pain then. That means I have to connect my master to my slave? Well, okay, that's not quite good. Let's think of a better way. Well, if I keep doing this, I end up instantiating 3 interfaces all the way down just to get to my driver. And it's going to be really chaotic connecting everything up. What if I could just pass a pointer of this interface into test, into the environment, down to the driver, and then the driver could actually control the signals. how could I do that? Well, what if I said virtual? Virtual is the keyword that says don't instantiate, pass a handle of this object. So what happens is, deep in my test bench, I go one layer into the I'm at the TB, and I have my Wishbone master instantiated. I'm going to go ahead, and for me to control the master from my driver, I need to pass a handle. So what I'm going to do is I'm going to pass a pointer or a handle using virtual to the test, and from the environment, or rather the test to the environment, I'm going to pass a handle again using virtual, and then again to the driver. And the driver then can control the signals just like we showed in the example here. It can control the signals just like this. It'll get a pointer to the Wishbone interface, and so if we look at this, it might look something like, now I have a virtual Wishbone, but it's still the same, and we might want to use a better name, you know, and we'll basically say Wishbone slave dot strobe, and we're still talking to the same interface. This allows us to create like levels of indirection and allow us to still talk to the top level test bench. Okay, so that's why virtual is very powerful.